Okay, so, oops, balance this thing. Okay, good. So I'm going to start talking about some stuff out of chapter 9, and what this is about is we talked before about equilibrium points and stability. And now we're going to talk about that again in the context of systems of differential equations. So let me ask you to recall, for a differential equation, y prime equals f of y, and I call this an autonomous differential equation. It's autonomous in the sense that the derivative of y is expressed only in terms of y. We don't see whatever the other variable is here, whether it's x or t or whatever. Y prime is just a function of y. And we find the equilibrium points by setting f of c equal to 0. And what those are is, those are values where if y were exactly that value, then it would stay that value forever. Because if we're talking about a value c where f of c is 0, if y is that value, then this is like saying that y prime would be 0, meaning y is not going to change from that value, meaning it's going to stay at that value c forever. And we characterize equilibrium points as either stable or unstable, and we drew pictures like this. A stable equilibrium point, if I draw this picture, this is a phase diagram, that's what this is called. If the arrows are pointing in, then it's stable. If they're pointing away, then it's unstable. Actually, if even one of them is pointing away, then it's unstable. So yeah, sorry for the review, but we talked about all of that before. We're going to talk now about equilibrium points of a system. So let's talk about a linear system. That's really the only kind we talked about so far. And I'm going to write down what maybe looks like an analogous thing, like an autonomous system. These are the types that we've been looking at anyway, where, say, x1 prime is this function of x1 and x2, x2 prime is some other function of x1 and x2, and these are linear. It's just a, b, c, and d are just some numbers. And this is the type of system that we've also been writing it this way, like the vector x prime equals a times x, where A would just be this 2 by 2 matrix, A, B, C, D. Right? And yeah, so let me make it clear, I guess. This always has the equilibrium point zero, zero. And what do I mean by that? I mean it in the same sense that I was using it before, meaning like if x were to take this value, if it were to be this point, then it would stay at that point forever. Why? Because if I'm at this point, x1 is 0 and x2 is 0, and I plug that in here, this tells me that x1 prime would be 0, meaning that x1 is not changing. And this would tell me that x2 prime is 0, meaning x2 is not changing, meaning it would just stay at that point forever. So that's the sense in which this is an equilibrium point. And let's talk about the stability of that. And this is convenient because we know what form the solution to this type of system would take. This is the type of system that you solve the way we've been doing it, where you find the eigenvalues and eigenvectors and you do what you do. So just to recall some of that, there's the sort of normal or easy case where you have two real eigenvalues and each, like, say, lambda 1 corresponds to v1, lambda 2 corresponds to v2. This could also be the case where maybe lambda 1 and lambda 2 are the same, so you have a repeated eigenvalue, and usually you have two different linearly independent eigenvectors still, v1 and v2. So it can be like that. We also talked about what you do with complex eigenvalues, and if you are maybe not remembering this that well, this is from 7.3. This is just a formula. This is the case where, actually, let me find it so I can show you. This is the case where you have complex conjugate. Yeah, it's this case. You have complex conjugate eigenvalues like p plus qi and p minus qi. And you have complex conjugate eigenvectors, a plus bi and a minus bi. And it was just this formula. That's all I wrote. That's all I wrote. And then there was a weird case, like, and this is out of 7.6, and this is the case where you have a repeated eigenvalue, but you don't have two linearly independent eigenvectors. Like, this is what we called a defective matrix, and I just wrote like what we do with that. For this one, v1 is an eigenvector corresponding to the eigenvalue lambda 1. v2 is not an eigenvector. v2 is this vector that was the result of this funny thing we were doing in 7.6. If you don't remember, you can review 7.6. But v2 is this other vector that we came up with. And the solution took this form. So let's not worry too much about every aspect of this. I just wanted to summarize the different forms the solution can take. Let me summarize that as follows. What I'm interested in right now is this equilibrium point, 0, 0. And roughly speaking, I know that I have not formally defined the notion of stability yet, but sort of intuitively, I would like to talk about the stability of that equilibrium point. And intuitively, what does stability mean? Stability means if I'm close to it, then I'm moving towards it. Unstability means if I'm close to this, then I'm moving away from it. Just roughly speaking. So let's talk about these types of solutions and what they do. Do they move towards the point 0, 0, or do they move away from it? So the observation is that all of these move towards the 0 vector, the point 0, 0, the same thing. They all move towards the 0 vector if the eigenvalues have negative real parts, like this one. In this case, the eigenvalues are both real, so the real part is the same as the eigenvalue itself. So if lambda 1 and lambda 2 are both negative, then you have like e to a negative number times t, which is going to 0 as t goes to infinity. So this is a number going to 0, this is a number going to 0, and as t goes to infinity, this approaches the zero vector if lambda 1 and lambda 2 are both negative. This one looks more complicated, but the important part is, again, you have e to the pt here. And this is why we said if the real part of the eigenvalue is negative, p is the real part, because the eigenvalues here in this case are p plus or minus qi. That's what these two numbers p and q are. So if p is negative, then what you have is this exponential decay. This thing inside here is just a periodic like vector function. Like it's just sines and cosines. So if this number is going to 0, 0 times this periodic thing is going to the 0 vector. And likewise with this is another, we have exponential decay here times this periodic thing. And yeah, actually, as I'm talking about this, I should also show you, because there's this section that I skipped, 7.4, and I'm still mostly going to skip it, but it has a lot of neat pictures of how the solutions to these 2x2 linear systems can look. And what I'm talking about right now, like this kind, where you have complex conjugate eigenvalues with a negative real part, let me describe it real quick again in the same way I did. We have exponential decay times this periodic vector function. This periodic thing in parentheses and also this one, they're basically tracing out an ellipse. That's what you get if you take like a vector times a cosine and plus another vector times a sine and graph that. You're going to get the graph of an ellipse. And here, like this picture. With this e to the pt out here, and if p is negative, then we have like this scalar on the outside that is multiplying by this, which would normally be tracing an ellipse, but this is making it get smaller and smaller. So it's like this. It's one of these that spirals inward. It's sort of, very roughly speaking, like an ellipse, except also going inward. As you go around, you go inward. Meanwhile, if you had the same thing except the eigenvalue had a positive real part, so that the e to the pt is actually going to infinity, then you spiral outward, like it's going farther and farther out as it goes around and around. So yeah, I encourage you to take a look at these pictures in 7.4. Of course, I'm still mostly skipping 7.4 because it goes into way more detail than I really intend to go into about this. But it has a lot of really nice pictures to help you visualize this stuff. Anyway, I was explaining this summary. So right, I think maybe this first star is believable at this point. Also, I'm not going to talk too much about this weird case, but you can check the weird case. It works for this as well. If the eigenvalue, if lambda 1 is a negative number and t goes to infinity, this does approach the 0 vector. Meanwhile, the second star is sort of just saying, well, it's like the counterpart to the first star. These solutions, so to speak, they blow up, meaning it's a vector whose magnitude goes to infinity. If any of the eigenvalues has a positive real part, right? The first thing we said about approaching the zero vector, that's only true if both eigenvalues have negative real parts. If either of them has a positive real part, like if lambda 1 were positive, then this term would blow up, even if lambda 2 were negative. So if either of them is positive, then this vector blows up. Similarly, for this one, I described this one, if p is a positive number, then that's like it's spiraling outward instead of spiraling inward. And let's ignore the weird case from now on. Except, actually, let me talk about the weird case before we finally ignore it. How weird is this weird case? It's extremely unlikely to occur in just random instances of differential equations that arise from real life. So here's how unlikely it is. You can think of your, if you think of your matrix as like a random matrix, its eigenvalues are, for a 2 by 2 matrix, its eigenvalues are, you can think of them as essentially two random numbers. It's extremely unlikely that either of your two eigenvalues would be 0. It's even less likely that they would both be 0, and that's the weird case. But even weirder than that, even if both of your eigenvalues are 0, you usually still have two linearly independent eigenvectors, which would fall under the first case. So the weird case is really when you just have a repeated 0 eigenvalue, like when this isn't positive or negative, because we know what happens if it's positive or negative. If it's positive, it blows up. If it's negative, it goes to 0. So the case that we're really not going to talk about is when you have a repeated 0 eigenvalue that is defective. Furthermore, defective in the sense that it does not have two linearly independent eigenvectors. And that's a case that it's a pretty weird case. So we're going to ignore that from now on. So to summarize, except for the weird case, I would describe these all as stable if the eigenvalues have, if the real parts of the eigenvalues are less than or equal to 0. Even if the real parts are 0, I would describe it as stable because the solution, at least it's not blowing up. At least the solution is not a vector whose magnitude is going to infinity. If the real parts are 0, if these real parts are 0, like this is when the eigenvalues are real, if these real parts are 0, then these would just be constants. Down here, if p were 0, then that's just when I have just the ellipse. That means the graph of the curve is just an ellipse. And formally we consider that stable because it's not moving towards 0, but it's also not moving away from 0. And in this context, we call that stable. Anyway, I'm going to do examples of this, so this was a lot of theory, and the video is just about 20 minutes long now, so I'd better upload this and make it a new one.